So this is my lab report for the first lab for this class. So the purpose of this lab is to understand the concept of charge using charge tapes, observe its interactions with its surroundings, and determine the amount of excess charge on it. So to do this, we will use Coulomb's law for electric force, which states that the electric force is proportional to the product of the two charges and inversely proportional to the square of the distance between them. We'll also use Newton's second law, which states that the net force of the system is the rate of change of its momentum, and the force of gravity, which is that mass times gravitational acceleration gives you the force. So the results of this experiment show that the charge tape is attracted to uncharged objects, repelled by another charge tape, and has a positive net charge. And its charge is in the order of magnitude of 10 to the negative 8 coulombs. The fraction of atoms on the surface that have been gained or lost, an electron, is 10 to the negative 7. So the assumptions for this experiment is that the amount of charge on a tape stays roughly the same. The tape doesn't get affected or discharged when exposed to air. The tapes can be modeled as point charges concentrated at the center of the tape. All the excess charge is evenly distributed on its surface. Both the tapes have the same amount of charge, and the mass of the tape is approximately 1 gram per meter. First, we start with a qualitative experiment to observe its interactions. So to do this, we charge a piece of Scotch tape by sticking one tape flat on a table, sticking another on top of it, ripping it apart so that it gets charged, sticking it to the edge of the table, and then observing its interactions. When you bring your finger close to it, bring an uncharged object close to it, bring a second charged tape close to it, and bringing a charged plastic pen close to it. So the observations noted are that it is attracted to uncharged objects, such as my finger, which indicates that the tape is charged and it induces an opposite charge on the uncharged objects. It is repelled by the second charged tape, which means that both of them have the same sign of charge and thus repel each other, and is attracted to the charged pen. The plastic pen has a negative charge, and so the attraction means that the tape has a positive charge because opposite charges attract, and thus there is a deficit of electrons on the charged tape. Next, we can perform a quantitative experiment to determine the amount of charge on the tape. So to do this, we create two charged tapes and suspend one of them between two neutral objects. Then, we take the second charged tape and hold it below the first one. This should repel the first one, allowing it to hover slightly. We can thus measure the distance at which it starts to hover, the length of the tape and its width, and thus calculate the charge and the fraction of excess charge on the tape. This is better represented using a free body diagram. Here, A and B represent the tapes, which can be modeled as point charges, and B, representing the tape on the top, is our system, and A is thus its surroundings. A exerts a force, FEB, on charge B, an electric force, and B also experiences a gravitational force. Since the momentum of the system is not changing, the electric force and the gravitational force are equal to each other by Newton's second law. And assuming that the charges on each tape are the same, we can thus rearrange the equation to find the charge QB on the upper tape. We can calculate the fraction of excess charge by finding the ratios between the surface area of the tape, the surface area of the atom, and the number of excess electrons, giving us the equation at the bottom in the red box. Substituting the numbers that we gained in our experiment, which are all listed here, into the formulas highlighted in the red box in the previous slides, we get that the charge on the tape is roughly 1.2 times 10 to the negative 8 coulombs, and the fraction of atoms with excess charge is roughly 4 times 10 to the power of negative 7. We can also achieve this using a computational model. First, we define our constants, including Coulomb's constant and the gravitational acceleration, as well as our experimental constant, such as the measured distance between the charge tapes and the mass of one of the tapes. We can then write a function to calculate the electric field felt by the top tape because of the bottom tape, and thus use that to calculate the force of electric force by the top tape, as well as the charge of the top tape. This is the code that allows us to visualize it by modeling each of the tapes as a spherical point particle and showing the forces as arrows. And here are the results and visualization of the coding. Thus, in conclusion, we find that the charge tape has a net positive charge on the order of magnitude of 10 to the negative 8 coulombs, and about 1 in 10 million atoms has a deficit of electrons on the tape. So the possible source of error for this experiment lie mainly with the assumptions we made. For instance, the tapes may not have had roughly the same amount of charge, and they may have been unevenly distributed on tape. Furthermore, it was difficult to measure the separation distance and the mass of the tape without using a precision scale or using stable rulers, so it's not highly accurate. Additionally, the tapes could have been discharged due to changing humidity in the air. Nevertheless, this experiment did give us a result on the order of magnitude of 10 to the negative 8 coulombs, which agrees with the values found in the textbook. So So what if the electrons had a positive charge and the protons have a negative charge? Well, nothing would change because the property of opposites attract and like charges repel stays the same. So both charge tapes would now be negative instead of positive and would still repel each other, and they would still induce opposite charges on uncharged objects and thus still attract them. Why is it important to handle the charged tapes as little as possible? This is because the more we handle them, they get discharged. The ions in our blood and skin allow the human body to act like conductors, so the excess charge flows into the tape as electrons to replenish the charge deficits, thus making them charge neutral.